Dear students, let me share the screen. In this video lecture, let us discuss on the concept of frequency resolution in discrete Fourier transform. The point of discussion here is, if we have any signal x of n, okay, let this be a signal of length n, okay, and if I apply or take DFT, discrete Fourier transform, what I get is a sequence again x of k, where k is also of length n. Okay, so if I sketch them, I will have some frequency quotient. Okay, so I can consider from minus n by 2, okay, to n by 2. Okay, if n is even, I can consider like that. If this is of n minus 1 by 2, okay, n by 2 minus 1. Okay, and however, these in DFT, what you see are only samples, and there is no clear information on frequency associated with these samples. That means, say this is first sample, assume that, and there may be second sample, and so on. Between these two samples, how much is the frequency in hertz? Okay, that corresponds to the frequency contained in the original signal x of n. Or, so if a signal has, a DFT has, assume that only two peaks. Okay, when I consider from minus n by 2 to n by 2 minus 1, assume that there are some peaks at, say, minus n naught and n naught. Okay, but however, these peaks may correspond to some frequency in the original signal. What is that frequency f naught corresponding to the original signal that corresponds to this peaks? To understand this concept, what we need to see is, we have to start from x of t, the analog signal, wherein you may have something like cos 2 pi f naught t, and after a series of operations like sampling and then taking some samples of the sample signal and finding DFT, you will be getting this spectrum. So during that process, there are a couple of operations that are happening, okay, that will guide us to tell what these peaks or the sequence number or the sequence index wherein we get the peaks corresponds to which of the frequencies. Okay, so n naught is seen in the DFT. If you see DFT, it's only a sequence of numbers in frequency domain. Okay, but what those sequence of numbers corresponds to which frequencies, or the strength of these all corresponds to the strength of different frequency components in the signal x of n or x of t, to which f continuous domain frequency components do they correspond to? That's the question. Okay, the idea is to map k to f. Okay, and how to map k to f? That is the question that we are discussing. This helps us also to understand between two samples what is the resolution delta f. Okay, so the sequences are the sequence one like one sample gap in k equal to 1 implies what is delta f? Continuous frequency implies what delta f is that. Okay, So that gives the information about frequency resolution. Okay, so if I have this information, what advantage do I have? See, in the input signal x of t, okay, assume that there are, say, 2 cos 2 pi f naught t plus cos 2 pi, okay, f1 t. Assume that f1 minus f naught, okay, is equal to some, say, some value. Oh, so delta, I say that delta. Okay, so if this delta is very small, and if I do this process of discretization and finding FFT with some n points, the question is, can I identify this delta? Okay, can I identify this delta? Okay, at two different samples in the frequency domain. Okay, so can I distinguish this delta as, okay, delta k change in at two different samples, or will this frequency gap merges to a single k? Okay, okay, this can be clarified if I know the frequency resolution. If frequency resolution is very small, in sense that if I can distinguish even 0.5 hedges, then even if this f1 minus f naught is less than 0.5, okay, any f1 minus f naught greater than 0.5, I can distinguish here as at two different k values or two different discrete Fourier transform quotients. Okay, whereas if f1 minus f naught is less than 0.5, then I will not be able to distinguish here in the frequency domain. They both club and will appear at same index of k. Okay, this is what is given by frequency resolution. Given this frequency resolution, okay, we can also use the information so that to map k to f, and we can normalize finally the axis that we have here in terms of k, okay, to write in terms of f. This is referred to as frequency normalization. So the changing the axis from k to f is frequency normalization. Okay, is changing k to f. Okay, so that we can easily see which are all the frequency content present in the original analog signal. Okay, given the information of sampling time, sampling period, and so on, sampling rate, sampling period, and so on. Okay, this is the exercise now that we will be discussing, or this is the mapping or the that we are interested in. This is the information of frequency resolution that we would like to find out. Okay, let us take an example to do and understand this. So let us first take an example, simpler example. Say f of t, let it be equal to cos 2 pi into 300 into t. So this signal has a frequency content, say it has f naught is equal to 300 Hz. If you ideally see the spectrum for this f of t, okay, that is f of capital F of j omega. This is what continuous time Fourier transform. Okay, if you do this for this signal, okay, what you will be getting is this f of j omega. Okay, so that will have a peak at 300 Hz and at minus 300 Hz, right? Omega naught and minus omega naught, or 2 pi into f naught and 2 pi into minus 2 pi into f naught. Okay, you will have peaks at these locations, and the extent of peak may be half. Okay, so this is what is the frequency content. We can easily see here the frequency content in the signal. This axis now is simply f or omega. Okay, so this is crystal clear that we are able to see the frequency content in the axis itself. Okay, this is f of j omega. That is obtained through continuous time Fourier transform. I will write here continuous time Fourier transform. Okay, if you do this, what you are getting is this. Okay, fine. So now the question is, assume that I want to perform sampling. So I will give you sampling frequency as say some 800 Hz. With this sampling frequency, do you think aliasing will happen? It will not happen because it is greater than or equal to 2 times df naught, maximum frequency in the signal here. So no aliasing. Okay, it's good. So now let us write, if I do sampling, what will happen? I will get sample signal fs of t. Okay, so how does the sample signal look like? Cos 2 pi 300 into what we write here is n into t, okay, RTS, okay, and what we get is fs of n. I will write. So fs of t is, see, let me write the intermediate step before I move on directly writing the discrete signal. So I want to write fs of t. Fs of t is nothing but f of t, okay, multiplied with, okay, it's multiplied with what? Delta function, delta trine, which is where t minus ntf. Okay, where let this be yeah, n equal to minus infinity to infinity. Okay, this is what is the sample signal fs of t. So this you can write as n equal to minus infinity to infinity. Okay, f of t minus, so multiplication here becomes convolution in frequency domain. So fs of j omega, you can write it as f of, I am directly writing in frequency domain, f of j omega minus n into, here let us write k just to distinguish between the conventional n, k into fs. Okay, omega s I will write. Okay, so what is omega s here? So essentially the sample spectrum after sampling, okay, results in, how does it look like? It will also be 1, 2, 3, 4, 5, 6, 7, 8. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so it will keep repeating at omega s because you have sampled it. What I'm writing here is fs of j omega. Please note that I have still not moved on to the discrete signal because the information of the sampling period or sampling rate is important to me to derive or discuss the further discussion, to bring on the further discussions. Here it is omega s, 2 omega s, okay, and similarly here minus omega s. Okay, so you have here same signal at minus omega naught and omega naught. Okay, here again minus omega naught and omega naught. Okay, like this. So now if you see the signal, this minus again minus omega s, it keeps repeating. Where does it keep repeating? Okay, right. So now if, see, this is minus 300, and this 400. Okay, minus 4, 300, this 300, and this is 400 H. I'm writing here 2 into 2 pi. Okay, this is in what I'm writing here is in frequency. Okay, because frequency is what in terms of which we would like to understand. Okay, so now this is Fs in other words, and this is minus Fs. Where, sorry, Fs by 2, sorry, this is Fs and that is minus Fs. Uh, this is Fs by 2 and this is minus Fs by 2. Okay, so now if you want to see a cycle of this spectrum, okay, one period of the spectrum, this is the region wherein we will look at. Okay, so you see that this is exactly equal to this. Okay, the original spectrum. Okay, the content of this can also be seen from the in the original spectrum, or the original spectrum can be seen in this period. Okay, however, now because of the sampling, it is repeating. Okay, so now the next question is, if we want to get the discrete signal, we are not very happy just with this. Okay, from here, what we want to do is we want to get f. Okay, f of n we want to write. Okay, so we want to write the signal itself. So if you want to write the sample signal, what do we do? So this sample signal keep repeating. So cos 2 pi into 300 into t is replaced by nts. Okay, so which is cos of 2 pi into 300 by 800, okay, into n, or cos 2 pi by 8 into, okay, so this is what is the signal. Cos essentially 3 pi n by 4. Okay, so this is what is the signal. So now if we would like to sketch this spectrum, okay, so what we do is discrete time Fourier transform that we find. Okay, so here what we have seen for this sample signal, since it is we all here also we have found this also continuous time Fourier transform. Whatever we have plotted here is still the continuous time Fourier transform. Okay, so whatever you have here is continuous time Fourier transform of Fs of t. Okay, is what is this? Okay, right, because the convolution happens, you are able to see this repeating. Fine, now let us see the relation between this and this. Why I am discussing all this? Now when we find here the discrete Fourier transform, so from here if you want to go to the frequency domain, what I do is f of j omega, e power j omega. Okay, so this f of e power j omega will bring it into through discrete time Fourier transform. Through this discrete time Fourier transform, what's happening? Already here the information about capital T, okay, is lost because there is a periodicity that comes in. Okay, so there is a mapping that's happening here between there is no explicit frequency like sampling period and sampling frequencies that indicated in f of e power j omega, because its principal range is only from minus pi to pi. Okay, it repeats from minus pi to pi, whereas the f of fs of j omega repeats between minus omega s by 2 to omega s by 2. Okay, so there is a mapping happening here between these two things. Okay, when I move on to the discrete time Fourier transform from continuous time Fourier transform. Okay, because this is a discrete signal, doesn't have explicitly the information of fs retained. Okay, because of the periodicity of the cosine signal itself, or because of the sampling itself. Okay, so this now what we would like to see is So this mapping here, there is no particular, this is discrete frequency. The first one, it is discrete frequency. Second one is analog frequency. So this is the critical step for mapping the analog frequency to discrete frequency, or K to F later. Okay, we will see that in the next slide. So let us assume now that, okay, so you have actually F S of t, okay, that is anyway cos 2 pi into 300 into t. So let me write explicitly in terms of this dot star, that is multiplication with a sigma trine delta t minus k. I'm writing here t, capital T is 800. Okay, k equal to minus infinity infinity. Okay, for this what we had was fs of j omega, okay, which is nothing but f of j omega convolved with, okay, delta of j omega minus k times omega s. Okay, hope you remember this discussion that we had in the class, and this gives rise to, let me take 0 here. Okay, this is 800. I'm writing the axis in F here just for simplicity or direct understanding. Minus 300. Sorry. Okay, it repeats again around 800. So this is the spectrum, base spectrum that we have. And this is minus fs by 2 to fs by 2. Okay, so you can see that fs by 2 to minus fs by 2 is the one period of the spectrum. And this repeats again at fs, around fs, as you know. And the repetition is again comes exactly in the same way. Okay, and so on. I am not writing the rest of the things. Okay, but please assume that they're all there. Okay, so now this is in frequency axis. This is still in analog domain. Now when we switch over to the discrete domain, that is when we have here f of n, what we have is cos 2 pi cos nt, all that 2 pi into 300 into n by 800. So that we have got as cos 3 pi by 4, okay, into n. Okay, that's what we have got as n. And we would like to take now discrete time Fourier transform here, okay, and get the spectrum, that is f of e power j omega. Okay, because this is a discrete time Fourier transform. Now if you see the spectrum, okay, so it will also span exactly like, it will also be like this, but there is a normalization that's happening. So this is what is critical for understanding the frequency normalization, or the mapping the discrete to continuous frequencies. Okay, so now here it repeats with period 2 pi, as you know, and this period 2 pi is exactly equal to, okay, omega s here. Here it is omega s or fs. Okay, I'm writing these things. Let me write in the same color to understand. Okay, this is all fs or omega s. Okay, this gets mapped to 2 pi here. So 2 pi is in sense equal to fs in continuous frequency. Right? You understand? So whenever I say in discrete frequency, it is equal to fs in continuous frequency. And the other things follows. So this is fs by 2, pi is equal to fs by 2. Okay, and minus phi is equal to minus fs by 2. Okay, so and then where does the spectrum repeats? It also repeats like this, around 2 pi. Okay, same thing is the other side. Okay, this is minus 2 pi, and again here it repeats, spectrum repeats. Okay, so we are not bothered for the rest of the durations. So please note that the same spectrum is there, but there is a normalization that has happened through the process of discretization here. What's happening here? Fs of t to, or f of t to f of n, when there's a discretization. Okay, so there is a axis normalization that has happened. Okay, so this process gives in, so this mapping. So please note or understand this mapping. This will be critical for us to discuss the rest of the aspects. Okay, so from discrete time Fourier transform to continuous time Fourier transform, this is the mapping happening. Wherever if I say fs, please relate it to 2 pi. Okay, this should be or say whenever we say pi, it's equal to fs by 2. Okay, right? Now, given this f of e power j omega, what we do to get the discrete Fourier transform is, see, assume that f of n is given to us. I may take, say, n samples of it. Okay, n may range from n minus 1. This n may be different from the number of samples I need. See, for example, if I want to span over whole number of samples here, sampling frequency, if I want to quantify, it's equal to, in some sense, it is equal to ns. Okay, ns is equal to fs. That is, assume that if I say that sampling frequency is 800 Hz, okay, 800 Hz means that I'm taking 800 samples, okay, per second. That means the number of samples per second, if I denote it as ns, then what I'm essentially doing is I'm taking 800 samples per second. Okay, that's what is happening in the continuous time, or when I'm doing sampling. Okay, whereas when I take a finite signal, the number of samples I take in the finite signal need not necessarily be ns. Okay, they can be less than ns, more than ns, or exactly equal to ns. Now the question is, if I take exactly equal to ns, then what is the and what is the frequency resolution? If I take more or less than ns, what is the frequency resolution? To understand that, we should see that the discrete signal is only what we have at our hand. So to understand this better, we initially had f of t. Okay, in our hand, we had initially f of t. And then we did the sampling. We have the fs of t, still in continuous time. We have now f of n, only discrete time. Now, this is the initial signal. Okay, with frequency information. Okay, with analog frequency information. And this also has analog frequency information. However, this is discrete signal at hand. Okay, so this unfinite, when we apply DFT. Okay, so now the question is, this f of n is equal to, say, anyway, here in this example, cos 3 pi by 4 into n, fine. Okay, we may take n equal to 0 to, say, assume that I have taken only 300 samples. Okay, or I may have taken, in that case, n equal to, so let me take, say, in the first case, let me take 799 samples. In that case, n equal to ns. Okay, so this is case 1. Fine. In case 2, let me take, see, I can take any number of samples. what my objective is, after taking the samples, since this is only in my hand, after taking a certain number of samples, I will take now DFT. Okay, for this I will take, actually what I will do, discrete Fourier transform now. Discrete Fourier transform gives f of k, and this also has, okay, k ranging from 0 to only n samples. Okay, n minus 1 samples, so n samples. Okay, here also 0 to, I will say ideally, and here also ranging from 0 to n minus 1, so n samples. Okay, so in this case 1, n equal to ns. In case 2, say I may take 0 up to say only 400 I might have taken. Okay, or 399. Okay, in this case, n is equal to ns by 2. Okay, is less than n, say n is less than ns, and n equal to ns by 2. This is case 2. Okay, so in third case, I may take n equal to, say, I may take more samples. So assume that I took up to 1119, say 1199. Okay, so it's roughly n is equal to 3 times ns. Okay, 1200 samples I have taken. Sorry. Let me take 2499. Okay, so it's 2399. So 3 times ns I have taken. Okay, so n here is equal to 2400, which is equal to, okay, 3 times ns. This let it be case 3. Okay, so these are the cases to understand we will analyze. And in these cases, see, fk, the discrete Fourier transform, also has a spectrum that also has, actually the spectrum looks ideally like, say, it will have some peak somewhere. Okay, some at some index of, say, it may have at any index of say it may have at minus, okay, n naught and n naught, sorry, minus n naught and n naught, and this is k axis. Okay, so now what we want to do is we want to map this to f naught. Okay, how do I map? To map this, I need the information of ns. Okay, then only I will be able to map this. Okay, so now let us see how I can map given the information of ns in this example. Okay, so now let us take case 1. So now f of n is equal to cos 2 pi, cos 3 pi by 4 into n. Okay, and where n is equal to, n I have taken the number of samples that are equal to, okay, as you know, ns, we already know ns, so we have f of t, okay, and we use ns, f of t is with us, and we have ns is equal to 800. Okay, with this ns 800 we discretized and got f of n. Okay, and from here I took n is equal to ns. Okay, this is case 1. This is what we are seeing now. So let us sketch it now. See, I assume that this is 0. Since this goes up to, say, we are looking only one spectrum, this is DFT. Okay, so let assume that the DFT is also centered. So DFT also will have this k axis. So ideally it should have, so 8000 samples, because f of k is what I'm plotting. Okay, or mod f of k is what I'm plotting. It also have 8000 samples, 800 samples. But to make this, say, similar to whatever we had discussed earlier, let this be centered DFT. So it ranges from minus 400 to, okay, so 400. So just to make exact similarity, let us make from minus 399 to 400. Okay, so you can make either this way or that way. Okay, so now in this case, what we would like to see is where does the samples, the spectrum. But see, please note that you have taken ns samples, so there will be some peaks that occur somewhere. Okay, we don't know where they occur, but let's assume that they occur somewhere. Now the question is, see, if I take
what did we say, discuss before? Ns is same as 2 pi. So if I ideally map ns to 2 pi, this is minus pi and this is pi. And hence, this is again becomes 3 pi by 4. Okay, and this is whatever, say this, sorry, this is minus pi. Okay, this one is minus pi. And this is again minus 3 pi by 4. So I can easily see that, okay, the frequency content also here is 300. Okay, because this is 3 pi by 4. This is 400, this is 300. And this is minus 300. Okay, so I'm able to exactly get the frequency axis here. Okay, that is k is equal to f. The exact, it's equal to, say, or k, say wherever uh, the gap between two consecutive samples in the frequency domain, okay, is equal to, okay, is equal to 1 Hz. So that I exactly have the peak. Okay, wait, say if I have the peak k naught at k naught, which is equal to 300, it also is equal to f naught. Okay, so and this happened because the samples delta f is equal to, okay, 1 in k for delta f equal to 1 in k axis, 1 unit in k axis. Okay, that is why we are able to see that k naught equal to f naught, where the peak has occurred. This is still in k naught, please remember. And this in fact is equal to f naught in our simulations. Okay, in our example. Because the reason is ns equal to 2 pi and n equal to ns. Okay, so now this we say that here for this situation where the ns is equal to same as n, we have the frequency resolution in DFT axis is how much? Is 1 Hz. Okay, you have 1 Hz frequency resolution, correct? So now consider the next example. Now take f of n again. Let us take with another color. F of n again. N equal to 0 to only 399 samples. That is, okay, ns by 2, n equal to ns by 2. Okay, you have taken n number of samples equal to n. So in this case, what will happen? I again find DFT. Okay, when I find DFT, what I get is f of k. So this f of k essentially has to represent minus pi to pi range. Okay, irrespective of the number of samples I take, what it should represent is minus pi to pi. Okay, so what will happen because of that is this k is now, okay, only ranging from minus 200 to 200. But this should represent minus pi to pi. Okay, so once since it has to represent minus pi to pi, what will happen is that shrinking of the frequency axis will happen. So and hence, see, this whole thing now comes from, say, this is what this peaks will come at, say, minus 150 and 150 roughly. Okay, close to minus 150 and 150. Now, what I want to do is, I want to normalize this frequency axis. Say this is in k, this is in j omega. See, as you know, DFT is, say, DFS is, this is DTFT and this is DFT. So DFT is the sampled version of the DTFT. So now how I have sampled the sampling now, if you see, okay, that is so sampled such that 2 pi by n. Okay, this is the sampling. So if I have 2 pi is the total range that I'm covering, I am sampling with the sample range of 2 pi by n. Okay, so I'm taking a sample for each 1 by n gap. That's how I got these samples. Okay, so now, but however, the original spectrum has, okay, original spectrum has, if I want to get into frequency domain now, f, okay, f is what is the original. So I need to get here minus fs okay, plus Fs. This is the range that the continuous time Fourier transform has, okay, or the frequency axis that continuous time Fourier transform has. So to map from this K to F, what I do is the F is equal to, F axis is equal to, okay, what should I do? K axis, fine. So ideally I should get actually by N because number of samples into Ns. Okay, so what I'm doing, I'm normalizing with the number of samples I'm taking and multiplying with Ns to get the axis continuous time frequency here. Okay, please note that the continuous time frequency here, okay, is here it's at 150. 150 is say K naught here, and then F naught if I want to see here by this rule. Okay, what is F naught? F naught by this rule is equal to 150 K naught by N. That is how much? N is 400 into Ns, that is 800, which is equal to 300. That is correct F naught. Okay, so and hence this works as the frequency normalization axis when we consider the number of samples lesser than the lesser or more or equal than the sampling frequency in the signal. Okay, because the axis which with whatever n I take, that is DFT, that is sampled version of DTFT, and hence this spans over. So the number of samples, if they are 400, it goes only from minus, okay, minus n by 2 to plus n by 2. Okay, that is for k axis. Whereas for omega axis, it goes from minus pi to pi. Whereas for the omega, say capital omega axis, it is minus fs to fs, leaving out the, okay, 2 pi term. Okay, so that's how the mapping happens. To and hence to normalize, what we do is current k, whatever you have k index, by n, the number of samples you take at a particular f of n, okay, into ns. This is what is the frequency normalization term. Okay, for axis. Okay, so now given this, see what's happening now. Initially we had 300 H. Now it is appearing at k equal to k not equal to 150. What does it mean here? The frequency resolution, if we see, frequency resolution we see is how much? Is equal to each of the say two samples, k equal to 1. That means k equal to 1 sample, okay, delta f is equal to 1 sample in k. How much does it represent? That's equal to 1 by n into ns, or ns by n. That is equal to 2h here. Okay, so the frequency resolution here is, okay, frequency resolution here is 2h, right? Whereas the frequency normalization can be done by, okay, k into ns by n. So because delta k, the gap between each sample is 1 unit. Frequency resolution means 1 unit represents to how many, like how much, okay, how much in continuous frequency. That implies 1 unit in k axis is equal to 2h in continuous frequency, in f, continuous frequency. Okay, so that's what is frequency resolution. Fine. So now here you mean that 2h each sample represents, means that you will not be able to distinguish any frequencies that are less than 2h. Okay, so its frequency resolution is poorer than this. So this has better frequency resolution than this. Here also please apply the same formulas to get actually frequency resolution. So delta f here is equal to 1 into, okay, so it's 1 into n by ns, ns by n. Okay, that implies because n and ns are same, delta f equal to 1h. Okay, that's what we had on the frequency resolution discussion. Okay, whereas here there is no normalization term that's required because, okay, f axis is equal to, ideally equal to k by, okay, n into ns, where here you see that both are same, so f axis is equal to n axis, k axis. In this case, in case 1, this is in case 2. Okay, in case 2, you need to do frequency normalization to see the reflect the analog frequency on the axis. Okay, so now let's move on. This is case 2. So now I request you to do quickly on the case 3, wherein we have again f of n. Okay, initially f of t is there with us and sample with ns or fs is equal to 800 h. Okay, 800 samples per second and got f of n. And now f of n we take, okay, anyway same signal cos 3 pi by 4 n, take n equal to 0 up to 2399 samples. So here n equal to 3 times fs, ns. Okay, we have taken 3 times the number of samples. Okay, so in this case, what we would like to see is, so if this is 0, what will happen? We want to sketch in k-axis. So here, so the number of samples, it repeats from, so fn, so if you take discrete Fourier transform, what you get is f of k. Okay, this f of k goes from minus 1200 to 1200 samples. Okay, minus fs by 2 minus here n by 2 to n by 2. Okay, we just leave the extreme ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. Okay, up to here n by 2. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, this is minus ns by 2. Okay, minus n by 2, sorry. Okay, and here anyway it is 1200 and this is minus 1200. And where does the peaks occur? You can see that since this maps from minus pi to pi, because this is DTFT, DTFT is always minus pi to pi, whereas DFT depends upon the number of samples you take. Okay, depends upon n. Okay, n points. So depends upon n. And where does this map? So it maps again, this is 3/4 of this n by 2. So it is 3/4. Okay, so what you get, where you get the peaks will be 3 pi by 4, which is equal to, so here we have actually pi is equal to, so let's place here pi by 2, pi is equal to n by 2, 3 by 4 into 1200, which is equal to 900. Okay, so here 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, you will have one peak here. Okay, and then other peak here, right? Minus 900 and 900. Okay, so this is 3 pi by 4 and minus 3 pi by 4. Okay, this is where the peaks occur. Now the question is, I want to again map onto the continuous time Fourier transform. Okay, one period of continuous time Fourier transform of f. Okay, fs of t. Okay, one period of fs of t. And hence I want to get the axis in omega, like in omega. okay, in omega or f. Okay, so now the question is, what is the normalizing component? Okay, so as discussed before, the normalizing component is equal to the normalizing component, okay, for f is equal to, what is the normalizing component? Let me write this little up, omega s, okay, or continuous time Fourier transform. Axis we want to write, we want f is equal to k by ns into k by n into ns, because we would like to normalize first with n and then multiply with ns to get the corresponding minus pi to pi region or corresponding exact frequencies. Okay, so f naught now, if you just see here, f naught is equal to, so this is the normalization. This is what? Frequency normalization. Okay, this formula is same for all. Just substitute n and ns. Okay, in this case, f naught is equal to what? So ns is 800, n is 3 times of it. So k by 3, so 900 by 3, okay, which is equal to 300. Okay, you're able to see that and f naught is valid now. Okay, so this is how it maps. And then the frequency resolution, okay, this is anyway, please note that this is minus fs, okay, and then this is fs. What you get here is fs and minus fs. Okay, it has to be mapped to frequency resolution is equal to what? Delta f is equal to 1 by n into ns. Okay, that is equal to ns by n, in fact, which is equal to 1 by 3. Okay, in this case, what do we mean by frequency resolution being 1 by 3? It means that we'll be able to distinguish, okay, between two samples, okay, of say 1 unit difference. Okay, we will be able to 1/3 of the h, okay, we will be able to distinguish. Even if the samples f of n has two frequencies which are 1/3 frequency difference, still we will be able to distinguish in the DFT, because we have taken with large samples DFT. Okay, so that implies 1 unit in k axis is equal to 1 by 3rd h. So this frequency resolution is better. Okay, this is what is the discussion on frequency resolution and frequency normalization. But however, you can simply leverage this formula to perform all your operations to frequency normalize the axis changing from k to f. Also, you can use the frequency resolution with this formula. Okay, delta f equal to ns by n. Okay, so this directly you can use in your lab experiments. Thank you.